Hello, everyone. Welcome back to the course of Microcontroller Unit, MCU, Application Technology. Previously, we explored the use of MCU I/O ports and gained an initial understanding of MCU control functions through examples. Today, we will delve into a new and crucial concept in computer and MCU control fields: the interrupt system of MCUs. Next, we will explore the following aspects. Basketball is a sport familiar to all of us. During an intense game, if the referee's whistle suddenly interrupts the match, calling a foul on player number 15 and awarding 2 free throws plus 1 additional throw, the game is halted for the referee's decision. After the free throws are completed and the ball is reintroduced, the game resumes. This is a typical example of an interrupt process. First, let's define what an interrupt is and its concept. During program execution, if the system encounters an event that must be handled immediately by the CPU temporarily halts the currently executing program to address this event. This process is called an interrupt. The event causing the interrupt is referred to as the interrupt source. Interrupts are common in daily life and can be understood as more urgent matters that require immediate attention, thus pausing the current work until the urgent issue is resolved, after which the original task resumes. In a control system, there are many level events for devices whose requests or events need to be processed in a timely manner. Since the occurrence times of these requests or events are often unpredictable, handling them with software can be challenging, whereas using interrupts simplifies the implementation. While the main program is executing, if an interrupt source issues an interrupt request, the computer responds to this request by pausing the currently executing main program and executing the interrupt service routine, ISR. Once the ISR is completed, the computer resumes the main program from the breakpoint. This describes a complete interrupt process. The concepts involved include understanding that in our example, the foul is the interrupt source, and the referee stopping the game is responding to the interrupt request by halting the ongoing match to address the free throw process. The free throw process can be seen as the ISR. After the free throws, the game resumes. Interrupts can be nested. Consider a situation where the computer is currently handling an interrupt and executing the associated ISR. If a higher priority interrupt source issues a request during this time, the computer will pause the execution of the current ISR and respond to the higher priority interrupt request. This process is known as interrupt nesting. In daily life, this can be understood as having an even more urgent issue that needs addressing over a previously important one. The diagram helps to clearly illustrate the execution process of interrupt nesting. Next, let's examine the interrupt system of the Intel MCS51. The Intel MCS51 features 5 interrupt sources: 2 external interrupts, 2 timer interrupts, and 1 serial port interrupt. We can set 2 priority levels, 0 and 1, with 1 as high priority, enabling 2-level interrupt nesting. This table represents the interrupt source query program. Within the same priority level, the query sequence of interrupt sources follows the natural priority order. The microcontroller controls interrupts through several dedicated registers. First, let's examine the interrupt enable register, i.e. It is an 8-bit register, of which only 6 bits are utilized, rendering the remaining 2 bits non-functional and irrelevant for programming purposes. The highest bit in this register is the global interrupt enable bit, EA. A high level, 1, in EA allows interrupts to be processed, while a low level, 0, disables all interrupt requests. If EA is set to 0, no interrupt requests will be acknowledged. Under the condition that they are enabled, EX0, ET0, EX1, ET1, and ES control whether external interrupt 0, timer or counter interrupt T0, external interrupt 1, timer or counter interrupt T1, and serial port interrupt are allowed, respectively. All of these are active high. There are also the following registers: timer or counter control register, TCON. Serial Control Register, SCON. Interrupt Priority Register, IP. First, familiarize yourselves with the basics. We will cover the details in subsequent applications. Next, let's examine whether the microcontroller must always respond to an interrupt request from an interrupt source. The conditions for interrupt response are as follows. 1. An interrupt request must be issued by an interrupt source. 2. The global interrupt enable bit EA must be set to 1, allowing interrupts. 3. The interrupt enable bit for the specific interrupt source must be set to 1. If it is 0, the interrupt is masked. 4. No higher priority interrupt is currently being executed. 5. The current instruction cycle must be completed. 6. If the current instruction is a return instruction, the microcontroller must execute the next instruction before responding. The interrupt response process is illustrated in the PPT. Just like in a basketball game, where minor fouls or those missed by the referee go uncalled, the interrupt response process operates similarly. When programming in low-level languages like assembly, it is essential to grasp the interrupt response process. In high-level languages such as C, this process is abstracted away, and we only need to understand it conceptually. This refers to the previous example of controlling the shift register LEDs with a microcontroller. Let's examine the effect. Currently, we have added a switch to the external middle pin 0, GP 3.2. When the switch is not pressed, the effect remains unchanged. When the switch is pressed, all 8 LEDs light up. Releasing the switch returns the system to its original state. The control program is as follows. The color program has not changed. A new function void, inter0 interrupt 0, has been added, which is the ISR. Inter0 denotes the interrupt type, which is also the name of the ISR. Interrupt 0 specifies the priority of this interrupt source. The ISR is very simple. In the main function, an instruction, i.e. equals 0x81, which is 10000001 in binary, has been added. Referring to the interrupt enable I register, we know that this instruction enables interrupts. It allows external interrupt 0 by setting one of the enable bits, thereby permitting the occurrence of this interrupt. Let's observe the actual effect. The normal shifting lights up as expected. When the switch is pressed, all 8 lights turn on, indicating that the interrupt has been triggered. Releasing the switch returns the system to its original state. Note that the shifting does not continue from the position where it was interrupted previously. Today, we introduced a crucial concept, interrupts. Through a simple example, we have initially explored the application of interrupts. Consider this question: could today's case be implemented using software alone? Share your thoughts to deepen your understanding of the concept of interrupts. We covered many concepts today, so please review and reinforce the knowledge after class to facilitate future applications. Additionally, please complete the following exercises to consolidate the concepts learned today and deepen your understanding. That concludes this lesson. See you next time.